Hello, everybody. Welcome to today's webinar. This is going to be presented by Dr. Sohaila Shabani-Berki. Dr. Shabani-Berki obtained her PhD at Iowa State University, working with Professor Jaime Juarez. Her research was focused on microrheology and functional materials. She will be giving today's talk on accurately measuring high viscosity samples on m-VROC 2. And for this talk, she brings multiple years of experience and expertise. So with that, I hand over the microphone to Sohaila.
Thank you so much, Christian. Hello, everyone. Welcome into our webinar. I'm Soha, and today I'm going to talk to you about measuring high viscosity samples with m-VROC 2 and show you the capability of m-VROC 2 in handling high viscosity fluids. Before that, I will start with some quick background about the applications of high viscosity fluids and the importance of measuring viscosity. I will continue with a review of our VROC technology and specifications of m-VROC 2. Then I will talk to you about the features of m-VROC 2 software that allows us to choose the right chip for our measurement and design of experiment. Then I present viscosity data of various high viscosity samples. Last but not least, I will briefly go over the cleaning protocols and show you how to properly clean your chip after measuring high viscosity samples. People often use the expression thin or water-like for liquids that have low viscosity, and thick for liquids with high viscosity. Generally speaking, fluids with larger, more complex molecules will have higher viscosities. In polymeric fluids, the polymer chains can also become entangled with one another, forming networks that are able to trap water. So depending on the level of the entanglement, viscosity may increase. Viscosity is also dependent on concentration, and the relationship is not usually linear. For example, a small increase in concentration of a protein may increase viscosity a little, but once a critical concentration is exceeded, the viscosity can increase exponentially. High viscosity fluids are utilized in different applications. Recently, the interest in additive manufacturing of high viscosity resins is rapidly growing because of the wide range of potential applications and also the higher quality and better mechanical properties of the printed parts. In biopharma, it's been reported that the interest in developing high viscosity therapeutics, peptides, proteins are growing as well. The next application is in food industry. High viscosity fluids are found in food products such as proteins, hydrocolloids, or gums. You also can find cosmetic products in your daily skincare or hair care routines that uses high viscosity fluids. For example, skincare serums or moisturizers use hyaluronic acid as one of their main ingredients. HA, or hyaluronic acid, is a natural substance that is found in body fluids such as eyes and joints. In the next slides, I'm going to show you the viscosity of different molecular weight HA, and you will understand how viscosity can change with concentration and molecular weight. Now the question is that what we want to learn from viscosity measurements and why. Viscosity is an important parameter in processes or applications involving fluid flow. For example, in 3D printing, it's crucial because it affects the quality of final product. If the resin is very high viscous, it can cause clogging and uneven extrusion. On the other hand, low viscosity resins can lead to poor adhesion. Printing of resins up to 5,000 centipoise has been researched. In biopharma industry and particularly drug development, viscosity is critical parameter for screening candidate drugs in the early stage development. In the final steps, however, viscosity is used to determine the injectability, and with that I mean the maximum injection force limit that ultimately is used to evaluate the ease of injection or the delivery of drugs into the body. Manufacturability of a product is highly dependent on the viscosity. Any fluidic system can be highly shear sensitive, and the structure can break down with the applications of shear, as is the case, for example, during mixing or when pumped through pipes. So the flow behavior of products is important both during processing as well as for manufacturability. In food products, viscosity is also a characteristic of the texture of the food. This means that the viscosity of a product must be controlled and measured in production so that each batch is consistent from day to day. Viscosity measurements can also be used to evaluate the stability of a product. That include storage stability or aging stability, shear, and temperature stability. Generally speaking, viscosity of a product is an important parameter as it can be used as an indicator of quality of the product, and it is an essential component of quality control. Now that we learned about the importance of viscosity, I'm going to introduce you our m-VROC viscometer and talk about its capability in measuring different samples with a wide range of viscosity. m-VROC is our newest viscometer with many upgraded features that enables accurate measurement of viscosity. Here you are seeing the top view of m-VROC and the main components that includes syringe, chip, VROC chip, and reservoir. m-VROC has the capability to retrieve the sample when it's needed. As you see in this animation, the moving part, which is called pusher block, moves and pushes the sample into the chip. When there is not sufficient sample in the syringe for the subsequent measurement, it would retrieve back the sample first and then run the next measurement. So this feature allows you to maximize your data and do unlimited measurements with one loaded volume. The final retrieval is called recovery, in which the system will recover the sample into the syringe. This way, you can save your precious sample and use it for further characterization. Up to 80% of the sample can be recovered. Please note that after recovery, you may see bubbles or foam at the tip of the sample or at the meniscus, especially for the samples that stabilize bubbles like protein samples. Because the system tries to recover the sample as much as it can. So if you would like to use the recovered sample for the next run, it is totally fine, but please first remove those bubbles by pushing them out and then connect the syringe to your chip and set it up for the next measurement. Because the presence of bubbles in your sample can interfere with viscosity data and ultimately can lead to poor measurement. Okay, as I mentioned, up to 80% of the sample can be recovered. But please keep in mind that the recovery strongly depends on the viscosity of your sample. For lower viscosity samples, we expect to recover more. Also, all the Rheosens viscometers are closed system, which eliminates the effect of air interface or evaporation in your measurements. These are common issues in conventional rheometers such as cone plate or parallel plates. With that in mind, I want to talk to you a little bit about the core of our technology that we use for measuring viscosity. Our technology is called m-VROC technology, or Viscometer rheometer on a chip. The technology inside the chip is basically a combination of microfluidic and MEMS, or microelectromechanical systems. So we have a rectangular microfluidic channel where we have 4 pressure sensors that are located along the base of the channel, and they can measure pressure drop as the fluid flows through the channel. We control the flow rate, Q, and through the channel, and then we monitor pressure drop as the fluid flows across the pressure sensors. Since we know the geometry of the channel, we can calculate shear rate from the flow rate and the geometry of the channel. And also, knowing the pressure drop and geometry of the channel, we can then calculate shear stress. And shear stress divided by shear rate gives you viscosity. This is how we calculate viscosity. So we control shear rate, measure shear stress, and calculate viscosity. Since for today's webinar, our focus is on m-VROC 2, I summarized its specifications and listed in this table. Today, I am glad to officially announce that the minimum sample volume has been reduced to 10 microliter, which is the lowest among all the Rheosens viscometers. The minimum sample volume on m-VROC 2 used to be 15 microliter, but now we can measure viscosity with high repeatability with only 10 microliter of sample. So if you have costly or limited quantity of sample, then m-VROC 2 can fit your requirements. Also, we offer sample testing service, so you are welcome to send over your samples and then we will test them in-house. m-VROC 2 comes with 2 syringe configurations, 100 microliter and 2.5 milliliter. 100 microliter is typically used for low sample volume measurements. However, 2.5 is used for high shear rate measurements where more sample volume is required. On m-VROC 2, the maximum accessible shear rate has been increased to 5 million inverse second with the 2x pump configuration. With 1x pump, the maximum shear rate is about 2 million inverse second. The viscosity range that m-VROC 2 can cover is from something about 0.4 centipoise up to 100,000 centipoise. However, we are confident that we can measure the viscosity even up to 200,000 centipoise. If you have ever used our m-VROC 1, you may know that with m-VROC 1, we use water bath system to control the temperature. However, in m-VROC 2, Peltier temperature control is built in the unit that provides rapid heating and cooling rates and also a precise temperature control in the range of 4 to 70 degrees Celsius. I already talked about sample retrieval and recovery, so I skip for now. Barcode reader is also a new feature that allows you to simply scan any barcode and you do not need to manually type in the sample name in the sample name box. Chip cleaning station is included in the m-VROC 2 package, so that provides an automatic and ideal cleaning. The software is 21 CFR Part 11. That is the FDA's regulation for electronic documentations, which is essential to ensure the integrity and confidentiality of electronic records. So this way we can reduce the risk of data loss or unauthorized modifications. Also, automatic measurement protocols have been developed that allows you to measure your completely unknown sample. So without knowing the viscosity of the sample or guessing the viscosity, you can measure your sample. So this way, software and firmware can completely take care of your sample. So all the required cleaning protocols also have been designed and developed at RealSense, so you do not need to create any cleaning protocol for your samples, and we strongly suggest our customers to not changing or modifying any existing cleaning protocols. If you want to change it, please reach out to us so we can assist you with that. All right, so in the next few slides, I'm going to show you some of the features of the software, and you will see how we can take the most advantages of these features to get quality data from our measurement. In this slide, I'm trying to show you the configuration table that includes the information about the viscosity and shear rate ranges corresponding to any chip and syringe configurations. In the software, so you can find this table in the software under the measurement tab. If you click on this question mark next to pump, you will find this table. Now let's look at this table. I want to choose a chip for running my high viscosity samples. Say something from 1000 to 10,000 centipoise. Based on this table, for running such high viscosity samples, CO5, E05, and C20 are the ideal chips. With that in mind, I choose the right chip based on the viscosity of my sample. So this is very useful tool that allows you to choose the right chip for your application, so you can minimize the error in your measurement. Okay, now that I chose my chips, I want to create a measurement protocol that can handle my unknown samples, because technically I don't know the viscosity of my sample. For any user-specified or user-defined shear rate, an estimation of the viscosity of the sample is needed. But as I mentioned earlier, one of the most important features of m-VROC 2 is the automatic measurement protocols that can handle unknown samples and enables the accurate measurement of those samples. One of these automatic protocols is called level generator that you can see in this slide. We have preloaded or default level generator protocols for each configuration of chip and syringe. If you click on this drop-down menu next to protocol name, you can find those protocols. So you do not need to create one. So you can either use these preloaded protocols or create your own level generator protocol and customize it, like adding more levels or more shear rates to your protocol or set different temperatures. So more advanced measurement protocols can be created. Those protocols can be a combination of shear rate and temperature sweeps. They can be easily developed with level generator. And with those protocols, you can maximize the data with minimum sample volume. So to create one, you can go to protocol tab, measurement sub tab, and then click on level generator box. We actually added useful tutorials to the software. So if you click on level generator, it will be popped up and show you the step-by-step instruction on how to create the protocol. Just follow those steps and create the protocol. In the level generator protocol, the first 4 steps are called priming. That is essentially required to wet the chip and prepare it before the actual measurement. So the first segment after priming is 5% full-scale pressure, and it goes all the way to 95%. So the flow rates corresponding to these percentage full-scale pressure will be adjusted based on the viscosity of your sample. Level generator is typically used for a shear rate sweep measurement, where we want to determine the shear rate dependency of the viscosity. So this is an ideal measurement protocol for shear thinning samples. m-VROC 2 also allows you to create the protocol based on user-specified shear rates. For that, you need to guess the viscosity of your sample, or at least have an estimated value of the viscosity. Then you can use this range calculator tool to determine the minimum and maximum shear rate that you can run your sample at. With that in mind, now I'm going to go over the viscosity data that I collected with our m-VROC 2 and share some interesting results with you. This graph shows changes in the viscosity as a function of shear rate at a constant temperature of 25 degrees Celsius, collected for 3 different concentrations of hyaluronic acid with the molecular weight of about 3 million Dalton. I used level generator protocol, something like the one I showed you in the previous slide. The results clearly shows that these samples show highly shear thinning behavior. For example, the viscosity of the most concentrated one, this one, 0.75% HA, drops from something about 2,000 centipoise to about 3 centipoise, as the shear rate increases from 10 inverse second to something about 60,000 inverse second. Sorry, something about 600,000 inverse second. So to do further analysis on our data, we used Karo-Yasuda model to fit these non-Newtonian fluids. And in this graph, excuse me, is the power law index, and a parameter that describes the transition between Newtonian plateau and power law region. Model fitting actually is important across multiple fields and enhances your data analysis. You can use the constants generated by these fits to make decisions and perform calculations relevant for your samples. For these high concentration samples, we combine CO5 and EO5 chips to cover a broader range of shear rates, and it worked very well. Having 2 chips allows us to cover a wider range of shear rates. This graph shows the combined shear rate and temperature sweeps for the 0.75 weight% hyaluronic acid at 3 temperatures of 4, 25, and 70 degrees C. If you look at the data, you can see that at 4 degrees C, the viscosity of the sample at the shear rate of 10 inverse second is about 3,000 centipoise. That is quite high. But as the shear rate increases to about 600,000 inverse second, the viscosity drops to something about 5 centipoise. I must say that for reaching to these high shear rates, we used 2.5 milliliter syringe and loaded about 1.5 milliliter of sample into the syringe. So it is clear from the results that at all these temperatures, the sample shows highly shear thinning characteristics. And again, to cover a wider range of shear rate, the combination of CO5 and EO5 were used. Thanks to the sample retrieval feature, we only need to load the sample once in the syringe and then create and set up a combined temperature and shear rate sweep measurement protocol, click on the start button and leave the lab and do other tests. So I mean that the 1.5 milliliter sample is sufficient for doing such an extensive testing on your sample. And once you load and start the measurement, you do not need to stand by the instrument. Just leave it alone and it will take care of everything. Now let's step up and measure something even more viscous, something higher than 2000 and 3000 centipoise. Those can be measured with EO5 or CO5 chips. However, for measuring anything above 3000 centipoise, we need another chip. This graph shows the shear rate sweep viscosity data that we collected with m-VROC 2 and C20 chip for N4000 calibration oil. The lines represent plus and minus 2% of the reference viscosity. Oils are typically Newtonian, and this oil has the viscosity of about 11,000 centipoise at 25 degrees C. The percentage difference between the highest and lowest viscosity data is less than 1%. So it shows that the data is very accurate and it is still less than 1%, indicating the high repeatability of our measurement. As I mentioned, for this test, a C20 chip was used. I loaded about 90 microliter of oil into the 100 microliter syringe and could recover 60% of the sample back into the syringe. So if you have costly or limited quantity sample, there is no reason to be worried about your sample, because at the end of the measurement, you can recover your sample and reuse it for another test. For lower viscosity samples, m-VROC 2 is able to recover about 80 to 85% of the sample. With that in mind, let's look at the rheological behavior of a high viscosity sample that shows non-Newtonian characteristics. Here we tested high viscosity aloe vera gel with a C20 chip and combined the temperature sweep and shear rate sweep measurements to maximize our data with minimum sample volume. This gel is mostly used in skincare and haircare products. You may use aloe vera gel in your daily skin routine as a moisturizer, anti-aging, or makeup remover. Aloe vera gel exhibits highly shear thinning characteristics. That's why when you apply shear to the gel by rubbing it between your hands or applying it to your skin, its viscosity decreases, allowing it to spread more easily. This is one of the benefits of shear rate sweep measurement, since it tells us what the viscosity is at low shear and high shear rates. For aloe vera gel, for example, the viscosity at the shear rate of 3 inverse second is about 9,000 centipoise. However, when the shear rate increases to about 1,000 inverse second, the viscosity decreases to about 300 centipoise. So in practical terms, such high viscosity fluid with shear thinning behavior become easier to handle and process when subjected to shear forces. For example, in manufacturing processes where materials need to be mixed, pumped, extruded, or processed, shear thinning can facilitate processing. So understanding the shear thinning characteristic with minimal sample volume, like what we have done here, the shear rate sweep measurement with only 80 microliter of sample can be beneficial in optimizing production processes involving materials like aloe vera gel or any high viscosity fluids. Okay, now it's cleaning time. After the measurement is done, for regular samples that are less than 1,000 centipoise or 2,000 centipoise, we typically use our chip cleaning station to automatically clean our chip and reservoir. Thanks to the sample recovery feature, we can recover about 80% of the sample back into the syringe. This truly helps the cleaning process a lot. But in this case, since we are dealing with ultra high viscosity samples, running CCS cleaning right after the measurement may cause something what we call tunneling in the chip, because the recovery of high viscosity samples like aloe vera gel in the best case is about 60%, meaning that some sample is still left in the chip and tends to stick to the wall. And if we push a low viscosity solvent, it would flow in the middle of the channel. This is called tunneling. So, and this method may not be very effective for cleaning the chip. But if we add some sort of transitional step after the measurement and before the CCS cleaning, we can ensure proper cleaning of the chip. We call this transitional step the pre-CCS cleaning. All right, so the first step of cleaning process is to find a proper solvent. This solvent should be compatible with your sample. For example, the solvent that your sample is formulated in or your sample is miscible with. For example, MAP and protein samples are typically formulated in a buffer. So you can use that buffer as your primary solvent. For the pre-CCS cleaning, we load 100 microliter of the primary solvent into a 100 microliter syringe, create a measurement protocol, something like what you see in this slide, and run the cleaning solvent as a regular sample. Or you can also use the diluted version of your original sample and pump it through the chip instead of using the pure solvent. By that, I mean you can dilute your original sample, say by 50% or 60%, and run it through the chip. Everything is like running a regular sample. In this measurement protocol, I used a combination of automatic and fixed flow rate. There is no need to select the priming box because we here for normal measurement, for actual measurement, we select priming. But for this type of protocol, which that the purpose is cleaning, there's no need to select the priming box because we don't care about the data, right? We just need to clean the chip. So after that, I prefer to push the solvent into the chip at the highest flow rate. Solvents are typically low viscosity so that the flow rate can be set to 1200 microliter per minute, which is the maximum flow rate that a regular or 1X pump can provide. Then, due to the sample retrieval feature, we can push the solvent into the chip, pull it back into the syringe, and repeat this cycle for at least 20 times to ensure the proper cleaning of the chip. After the pre-CCS cleaning is done, then you can take the chip and reservoir and clean them on the CCS using the preloaded cleaning protocols. Choose the one that is compatible with your sample. For example, for cleaning MAB or protein samples, you can use buffer cleaning protocols. And again, for example, oil samples can be cleaned with oil cleaning protocols. So those protocols have already been developed in the CCS. So you do not need to create a new cleaning protocol. Okay, I think that's all for today. Thank you for your attention. With that, I will go over to the question section and see if you have any questions. Okay, meanwhile that we are waiting for the questions, I will just mention that anyone who signed up the webinar will get a recording at some point. If you don't have question at this time, but you think you might have one later, please feel free to contact us. Oh, I see a question. How long does the cleaning takes in average? Okay, the cleaning on CCS depends on the chip type. For example, C20, E05, or CO5, they can be cleaned in, say, 5-6 minutes. However, for EO2, since the channel depth is very small, that it takes more time for EO2 to be cleaned. So it depends on the chip type. Also, in the CCS, we have developed 3 levels of cleaning protocol for each type of cleaning. I mean, for buffer cleaning, we have 3 levels of low, medium, and high viscosity. So if you feel that your sample is low viscosity, you can use the low viscosity cleaning protocol. That takes less time. But if your sample is higher viscosity, you can use the high viscosity level, and that takes longer. So it depends on the chip type and also the level that you want to choose for cleaning. Okay, I will give 1 more minute to see if anyone else has any question. All right, I think I'm gonna end it today. Thanks everyone for joining us. Every month we have webinar. If you are interested, you can sign up and join our monthly webinar. Thank you so much.